All right, welcome everyone. Here we are at the second lecture of Chapter 3. We're going to continue talking about the cell. And in today's lecture, we're going to talk about how things get in and out of a cell, how things move around in a cell. So we're building on what we had in our previous lecture where we introduced what cells were and we looked at the plasma membrane. But before we dive into our new stuff, as always, let's start with our not really attendance questions and see if you can answer these. What is a chemical gradient? What is the primary component of the plasma membrane? What is meant by selective permeability? And what is the part of a solution that is dissolved? This is also the lesser component of a solution, the smaller component of a solution. So go ahead and pause the video, try to answer those, and hopefully you've done that. So let's take a look at these to see if we got them correct. First, what is a chemical gradient? Well, another term that you will hear that means the same thing is a concentration gradient. It just means there's more quantity of something in one area than there is in another area. Maybe there's more sodium in one area than there is in another. Maybe there's more glucose in one area than there is in another area. Those are chemical gradients or concentration gradients. Next, what is the primary component of the plasma membrane? The plasma membrane was mostly made of phospholipids. Remember, it was a phospholipid bilayer. It was made of those little guys that kind of looked like this, and they were all in a row. And then since it was a bilayer, there was another layer pointed in the other direction. And of course, there were other things. There were different types of carbohydrates, there were different types of proteins, but most of the plasma membrane was made of those phospholipids in a bilayer. Next, what is meant by selective permeability? We say that the phospholipid membrane, the phospholipid bilayer, the cell membrane, however we want to refer to it, we say that it is selectively permeable. So what does selective permeability mean? Well, we need to keep things inside the cell that need to stay in. We need to keep things outside the cell that need to stay out. But there are some things inside the cell that need to be able to get out. And there are some things outside the cell that need to be able to get in. And the cell membrane allows that to happen. It keeps the things out that have to stay out, but it allows the things that need to come in. And the ways that it does that, there's lots of different ways. But the fact that it can do that is called selective permeability. And last, what is the part of a solution that is dissolved? This is also the lesser component, the smaller component. This is called the solute. Remember, the solvent, which is usually, but not always, water, is the bigger component. It's what does the dissolving. The solute could be whatever is dissolved. Maybe it's salt. Maybe it's sugar. Maybe it's potassium. Maybe it's other electrolytes. Could be any number of things. But the part that is dissolved is the solute. Okay, now these today are very important questions. I asked these because today we are going to use all of these terms, all of these concepts that we learned either in the previous lecture or one of the Chapter 2 lectures. They are all going to come back and we're going to build on them. So if any of that we just talked about doesn't sound familiar or it's a little foggy, make sure to go back and review those topics before watching the rest of this lecture, because we're going to build on those concepts now. So, we just reviewed solutions. We said that solutions have solvent, usually water, not always, and that water was the solvent. It was the bigger component. And we have the solute, which could be any number of things, but it is what is dissolved. So here we see a beaker of some liquid. We're just going to say that it's water. And we see a little tablet, which is some sort of dye. Maybe it's something like methylene blue or blue food coloring or whatever. The water, in this case, is the solvent. The little tablet here of dye is the solute. And when we first put this little dye tablet in the water, there is a very high concentration of that dye right there, and a very low or non-existent concentration in the water. So we're going to look at something first called diffusion. And diffusion is the natural tendency for everything to move from an area of high concentration towards an area of lower concentration. Everything wants to move naturally from an area of high concentration towards an area of low concentration. Before we get into how this works, why this works, I like to tell people, imagine you are going into a gymnasium for some event, and everyone is crowded in one small corner of that gymnasium. Lots and lots and lots of people all packed into one corner of the gymnasium, and the rest of the gymnasium is pretty empty. Well, over time, those people are going to spread out. They don't want to stay all clustered together. They want to move out, so there's a little bit of breathing room, a little bit of room to move around. Well, people do that just because of comfort levels, but everything does that. And in lab, we're going to look at why this happens. But for now, we're just going to look at the gradient. When there is an area of high concentration and an area of low concentration, there is a gradient. There is we say a concentration gradient or a chemical gradient. Where there is high concentration and low concentration, we have a gradient that's going to cause these substances to move from high to low. We say they move down their concentration gradient. And even though this is going to be a lab topic, we're going to just kind of take a very, very brief look at why that happens. I'm just going to draw a bunch of little dots here, and these dots could be any solute. These could be salt, these could be sugar, these could be whatever. But over here, there's not so many. So here there is a high concentration, here there is a low concentration. Now, these little particles, whatever they are, they move around. They kind of vibrate. If we looked at them under a strong enough microscope, we would see that they kind of zigzag all over the place. This is called Brownian motion because it was discovered by a guy named Brown. Brownian motion. And if all of these little guys are kind of zigging around like that because of Brownian motion, when they're clustered together like we see here, they're going to bump into each other. And as they bump into each other, they're going to ricochet off in other directions, spreading out until they look more like this over here on the right side. That's what diffusion is at the microscopic level. The more clustered together something is, the more likely it is to bump into its neighbors and spread out. We go from high concentration towards low concentration, down its concentration gradient. There are other types of gradients. We'd mentioned them in the previous lecture. But right now, when we're talking simple diffusion, we are talking about concentration gradients, and everything moves from high concentration to low concentration. Now, in the cell, that happens too. And we're going to talk about what allows things to move around inside the cell, what allows things to move in or out of the cell, and there are things that are built into the plasma membrane that allow or disallow these to happen. So we say the membrane is selectively permeable, it has selective permeability, but permeability is going to be a big concept. What can get through the cell membrane versus what cannot? And there's three driving factors. The first is solubility of the solute. Well, things that are lipids, or things that we say are lipid soluble, things that dissolve in fat or things that are fat-based, the membrane is permeable to those. Remember, oil and water, fat and water, they don't mix. But oil and oil, fat and fat, they do mix. They are attracted to each other. And since the plasma membrane is mostly fat-based, things that are fat-based, things that are lipid-based, can cross the plasma membrane pretty easily. This is one reason why things like nicotine patches work. We'll get more into that when we talk about the skin, but nicotine patches and other types of medicine patches are lipid-based. Next, size. The smaller something is, the more likely it is to be able to pass through that phospholipid bilayer. The bigger something is, the less likely it is to be able to pass through. And last, the presence of carrier molecules in the plasma membrane, proteins. So if a cell wants something to be able to get in, chances are that cell membrane is going to have a carrier molecule for that substance for it to pass through easily. We'll look at some of these different types of proteins in a little bit. We saw them in the previous lecture. Proteins are very, very specific. We saw this at the end of chapter 2. They're based on shape, and their shape allows them to do one single job very, very well. It's all based on shape. If a carrier molecule is shaped to allow something to pass through, then that thing is going to be able to pass through either from the outside of the cell in or from the inside of the cell out. So carrier molecules increase permeability of the cell membrane to a certain substance. If we need a different substance to come into the cell, we would have a different carrier molecule. So here are some different ways that substances can cross the cell membrane. These, we say, are types of diffusion. Types of diffusion. First, simple diffusion. The basic type of diffusion, we say something moves from an area of high concentration to a low concentration, down its concentration gradient. That is simple diffusion. Simple diffusion can happen in a beaker, like we saw here, things move from high concentration to low concentration. You see the little tablet starts out in an area of high concentration. Over time, it starts to diffuse towards the area of low concentration. Given enough time, it has diffused enough that we have the same concentration throughout. Well, simple diffusion can also cross the plasma membrane from an area of high concentration to an area of low concentration. But not everything can. Here we see this is how lipid-soluble solutes cross the plasma membrane, because one of the things that affects solubility is if it is lipid-based. Here, lipid can cross the plasma membrane from an area of high concentration to an area of low concentration using simple diffusion. Next, carrier-mediated facilitated diffusion and channel-mediated facilitated diffusion. All facilitated diffusion means is we have diffusion occurring, but we are using some sort of protein to allow that diffusion to occur. Some things that are not lipids need to be able to cross the plasma membrane. They are either too big, or they're not lipid soluble, or whatever it is. So they cannot just diffuse through like we see over here on the left. That's not an option for them. So we have proteins. On the carrier-mediated facilitated diffusion, we have a protein that's closed, but when something binds to that protein, it causes it to change shape, and now it's open, so it diffuses inward. Remember from the last lecture of chapter 2, anytime we add something to or take away something from a protein, it changes shape. Here on this side, the protein is closed. It has a little opening on top, but it is closed. When we add something to it, let's just call this glucose because it looks like the way our book draws glucose. We add glucose to it. We have added something to this protein. Well, that causes it to change shape. And the way this one changes shape is it now opens up. When it's open, that glucose diffuses into the cell down its concentration gradient. But once we remove something from this protein, what's it going to do? It's going to change shape. Now it's open on top again for another glucose to bind. So that's one way that we can have proteins allow diffusion. A very, very similar way is something called channel-mediated facilitated diffusion. In channel-mediated, we have a protein that is always open. It's always open. It's like a tunnel. It's a channel. But it's a specifically shaped channel. Remember, proteins very, very specifically shaped to do a single job well. Here, this is another solute that is not lipid soluble, so it cannot diffuse through the plasma membrane directly. But there's a protein here that is shaped to allow this specific solute to come through. Nothing else can pass through, but this specific solute can. And it just diffuses down its concentration gradient, down its chemical gradient, from an area of high concentration towards an area of low concentration, but it does it through that channel. So facilitated diffusion, regardless of which type it is allowing diffusion down a concentration gradient using some sort of protein. And lastly, we have osmosis. Osmosis, at its most basic definition, is diffusion of water. Diffusion of water. It could be simple diffusion. It could be channel-mediated, facilitated diffusion. But it is diffusion of water. Most cells in our body have things called aquaporins. Aquaporins are just a channel protein that allows water to go through, but water can, to a small degree, diffuse through the plasma membrane. Not much and not easily, but it can diffuse through the plasma membrane. It does diffuse very easily through an aquaporin. So now we're going to talk about osmosis. What is the driving factor? When does it happen? And to do that, we have to talk about something called tonicity. So, before we talk about the terms for tonicity, hypertonic, hypotonic, and isotonic, we're going to do some drawing. And when we talk about osmosis, the best thing to do is use something that I like to call the aquarium scenario. So let's bring up our whiteboard. And draw out some different scenarios using aquariums and concentration. So here I have an aquarium filled with a liquid separated into two sides by a selectively permeable membrane. Now, if I say this is a selectively permeable membrane, that means that some things will pass, but other things will not. So we have to define what is this membrane permeable to. Here we are going to say this membrane is permeable to water and nothing else. Maybe it's permeable to sodium. Maybe it's permeable to potassium. In this case, it is permeable to water and nothing else. Sometimes you might just hear the term selectively permeable membrane, and they don't tell you what it's permeable to. In that case, it is permeable to water and nothing else. If it is permeable to something other than water, they will tell you what it is permeable to. So they will either say it's permeable to water or they won't tell you, but in both of those two cases, it's permeable to water and nothing else. So we have solution A on one side and solution B on the other side. And we're going to say that solution A is a 20% sodium solution. And we're going to say that solution B is a 30% sodium solution. Now, that's all the information that we are given. But even though that's all the information we are given, we automatically know a few things. First, if we say 20% sodium solution, just looking at solution A, ignore solution B for now. We say we have a 20% sodium solution. What else do we automatically know? Well, we know that if it is 20% sodium, the other 80% is solvent. Solvent. And for purposes of our class, solvent is water. So we have 80% water, 20% sodium. Now ignore solution A and let's look at solution B. We have a 30% sodium solution. What do we automatically know? We know that the other 70% is water. Make sure that makes sense. When they tell us the solution of something, the concentration of something, they are telling us the concentration of the solute. The remainder is the solvent. Now, the other thing we know is solution B has a higher concentration of sodium than solution A does. Solution B is more concentrated. There is more solvent on solution A. There is more solute on solution B. So now, looking at our terms that we saw a moment ago on our slide, let's bring it up just for a moment. Tonicity. We're going to use these three terms now: hypertonic, hypotonic, and isotonic. When comparing two solutions to each other, not a solution by itself, when comparing two solutions to each other, we are going to use those terms. The solution with greater concentration of solute, we say is hypertonic to the other solution. The solution with greater concentration is hypertonic to the other solution. So which one, A or B, has greater concentration? Solution B, because 30 is greater than 20. So solution B is hypertonic to solution A. Solution B by itself is not hypertonic to anything. Solution B is hypertonic to solution A because 30 is greater than 20. Now, solution A has 20. Solution B has 30. 20 is less than 30, so we say solution A is hypotonic to solution B. Solution A by itself is not hypotonic. Solution A is hypotonic to solution B. We are comparing the solute of one solution to the solute of another solution. We have to have those two solutions for them to be anything. Now, how do we keep that straight in our head? Hyper, hypo. Hyper is a root word that means above, more than, greater than, excess. A hyperactive child has excess active in them. They are very active. They are more active. Hyper has more. Hypotonic. Hypo is a word that means below, less than, under. A hypodermic needle goes under your skin. So now we have a solution that is hypotonic to the other solution, a solution that is hypertonic to the other solution. What if, and I'm not going to draw this out, but let's just say A and B both had 20%. Well, in that case, we would say they are isotonic to each other. Isotonic. Isotonic means equal concentration. If they both have the same concentration, they are isotonic to each other. They are not isotonic on their own. They are isotonic to each other. All right, so we've got the terminology out of the way. We've got our scenario set up. We see the different concentrations. What's the point of it all? Well, the point of it all is this is how osmosis works. And this is going to be very, very important if you are ever in a situation where you are administering IV fluids to someone. Because this is how you decide what fluids to give to someone and how they work. First thing is we said everything likes to move down its concentration gradient. So we look at the sodium in solution B and the sodium in solution A, and solution B has greater solute concentration. So solution B will see the sodium want to move towards solution A. But there's an issue there. Yes, sodium wants to move down its concentration gradient. Yes, sodium wants to move from solution B towards solution A. But it cannot. Why? Because the membrane is only permeable to water. So, the sodium cannot move from solution B to solution A because the membrane prevents it. Instead, what happens? Well, the water wants to move from solution A to solution B down its concentration gradient. And it does. Except that's not really why it's happening. There is a more important reason that will remain with us from this point all the way into your career. It will remain with us through Bio 137, through Bio 139, through whatever nursing or whatever career you go into. This is going to be a very, very important thing. Yes, water moves from solution A to solution B. But the reason that it does that, and if you ever move on, you will always know the students that had me, because I'm going to teach you something that will help you to remember this. And it will always stay with you. It's easy to remember. And all students that had me will shout this out at some point in a class. And that is, solutes suck. If you can remember that, it will tell you exactly what happens in these situations. Solutes suck. What does that mean? Well, if we looked at this concentration with the right kind of microscope, if we looked at this solution and we saw the sodium dissolved in it, we would see the sodium sucking water towards itself. All of these little sodium particles pull water molecules towards them because solutes suck. These sodium are sucking water towards themselves. And over here on side A, there's sodium dissolved there too, and it is sucking water towards themselves. This sodium on side A is sucking water towards itself. It is also sucking water from side B towards itself. Over on B, this sodium is sucking water towards itself. It is also sucking water from side A towards itself. So all of the sodiums are sucking all of the water towards themselves. They are pulling water towards themselves. But where is there more sodium? On side B. So who is sucking more? there is some water going towards A, there is some water going towards B, but more water goes towards B than goes towards A. Wherever there is more solute, wherever is hypertonic to the other, is going to suck harder. It's going to suck more water towards itself. So even though water is moving in both directions, water is moving more towards side B, the side with the greater solute concentration. Water will always move from a hypotonic solution towards a hypertonic solution because solutes suck. How long will the water continue to move? Tricky question, because every time water moves from A to B, A becomes more concentrated and B becomes more dilute. At some point, A and B will become isotonic to each other. It may happen quickly, it may happen slowly, but at some point, A and B will become isotonic to each other. At that point, what happens? Let's draw a new aquarium. Let's say it's the same aquarium, and we still have solution A and solution B, and we still have a solution inside. But now enough time has passed to where, let's just say we have 25% sodium which leaves 75% water. They are now isotonic to each other. A is not isotonic, B is not isotonic. They are isotonic to each other. Now, what happens here? Same concentration on both sides. It is really, really tempting to say, and now there is no movement. Now nothing happens. And if you look at it at a big picture, that's correct. A is not going to lose volume, B is not going to lose volume, neither of them are going to gain volume. But there is movement because solutes suck. Water is getting sucked towards side B. Water is getting sucked towards side A. It is just moving in both directions at the same rate. It's not that nothing's happening. It's just it's happening both directions at the same rate. So, let's go back and say tonicity. We've identified our terms. We've identified what happens in the aquarium scenario. But what about real world scenarios? Why is all that even important? Well, because this affects how fluids move in and out of cells in our body. If we were to take a blood cell, we see an erythrocyte here, and drop that cell into a solution that is isotonic to it, we say drop it into an isotonic solution, which I don't really like, because even though we say an isotonic solution, we are implying that it is isotonic to our body. It's just kind of bad form to say an isotonic solution. When you see an isotonic solution, it means isotonic to your body. Well, what happens? Water moves in and out of the cell at the same rate, so the cell remains at the same size. If we drop a cell into a solution that is hypertonic to our body, to our cells, Well, there's hypertonic, means the cell is hypotonic, more concentration in the solution, so the solutes are going to suck the liquid out. It's going to pull water out of our cells. Our cells shrivel up. We say that the cells are going to crenate. Crenate is the term for that. It's going to kind of shrivel up on itself. If we drop a cell into a hypotonic solution, that means the cell is hypertonic, so there are more solutes inside the cell. It's going to suck water into the cell, and the cell is going to expand. And if it expands enough, it will pop. We say that it will lyse. So depending on what we are wanting to happen with the cells, if we're wanting to introduce water or if we're wanting to pull water, then we give different types of IV solutions based on the patient. So this is extremely important if you're going into some program where you are going to administer IVs. Okay, we have talked about simple diffusion. And we've talked about other types of diffusion that collectively are called passive transport. Passive means that it does not require energy. Everything was moving from high concentration to low concentration without the use of any energy at all. When we see the term active transport, the active part means it's going to use energy. And remember, in our body, when we use energy, that energy is in the form of ATP, adenosine triphosphate. We saw that at the end of chapter 2. If that's not ringing a bell, please make sure to go back and review that. Active transport uses ATP. It uses energy. And the reason that it's using energy is to move something from an area of low concentration towards an area of high concentration. It moves things in a direction they do not naturally want to go. So, sodium is in a high concentration outside the cell. Every cell in our body. That is an important thing. It's going to come back multiple times this semester and next semester. The sodium concentration outside our cells is high compared to the sodium concentration on the inside of our cells. Also, the concentration of potassium is high inside our cells, but low outside our cells. Every cell in our body has high sodium outside, low sodium inside, high potassium inside, low potassium outside. Sodium needs to remain in a high concentration outside of our cells. And we have this guy called the sodium-potassium pump. And this is just a protein. It's found on every cell of our body. And even though it's this tiny little protein, it uses more energy than anything else in our body uses. It's constantly taking sodium from the inside of our cells and moving it out, and potassium outside our cells and moving it in. That's why we have such a high concentration of sodium outside the cell and low inside. It's why we have such a high concentration of potassium inside the cells and low outside. Because the sodium-potassium pump is using energy to push the sodium out of the cell against its concentration gradient and push the potassium into the cell against its concentration gradient. That is called active transport, and it's called primary active transport because it is using ATP directly to make this happen. It takes an ATP, it uses it, it pushes some sodium out, it pushes some potassium in. I'm going to go ahead and tell you this now. It will be important later in this lecture and later in the semester. It doesn't just move sodium out and potassium in. For every cycle, it uses one ATP. It moves 3 sodium out, 2 potassium in. Then it uses another ATP to move 3 sodium out, 2 potassium in. It uses another ATP to move 3 sodium out, 2 potassium in, and it does that constantly. 3 sodium, 2 potassium. Okay, let's look at something called secondary active transport. We said over here on the right side. Here we have a protein, and this protein wants to move glucose into the cell. And to move glucose into the cell, the way that it does that is one glucose attaches and one sodium attaches. This protein is built so that it will take a single sodium, a single glucose together and move them into the cell. Sodium is coming down its concentration gradient. It doesn't need any energy. Glucose comes along for the ride. What is not being used here? There's no ATP attaching here at all. It is just sodium and glucose binding to this protein. That causes the protein to change shape. Sodium and glucose come into the cell. Why is this considered active transport if there's no ATP being used? Well, how is the sodium able to come into the cell? It's coming down its concentration gradient. It's using a protein that doesn't use any ATP. But how is it coming down its concentration gradient? Why is there a concentration gradient even there? Because of the sodium-potassium pump. The sodium-potassium pump uses ATP to move sodium out of the cell against its concentration gradient, creating an area of high sodium concentration. What does sodium want to do? It wants to come back in to the cell. So even though this step over here does not use ATP, it depends on the previous step that does use ATP. So it is active transport. Primary active transport uses ATP directly. Secondary active transport doesn't use ATP, but it depends on a previous step that did use ATP. So it is still ATP dependent. It is secondary active transport. Let's switch gears for a second. I'm going to draw just kind of a very basic cell. Here's the nucleus. The nucleus has the DNA inside of it. Now, inside the cell, we have all of our different guys there, but we're going to look at a specific type of organelle called a vesicle. Vesicles are kind of like the shipping containers of a cell. They're like these little bubbles that have something inside of them, and they're always moving around inside the cell. So vesicles are what we're going to be looking at. Things that move into a cell sometimes will create vesicles. Not always, but sometimes. When something moves into a cell, the term for that is endocytosis. Endocytosis just means moving into a cell. Doesn't matter how it's doing it, it's just endocytosis. But there are different types of endocytosis. The first is something called phagocytosis. P-H-A-G, phage, means to eat. Phagocytosis is a term that means cell eating. And what happens is, let's just say there's a bacteria. There's different ways that this can happen. I'm just going to use the bacteria and your immune system as an example. There's a bacteria and there is a white blood cell. White blood cells move around throughout your body. And the way that they do that is they extend pieces of their cytoplasm called pseudopods, and they just kind of pull themselves along. And eventually, this white blood cell is going to creep up on this bacteria. It's going to extend these arms around the bacteria. Eventually, these arms will close around the bacteria, and the bacteria will be trapped inside of a vesicle that formed there. This is phagocytosis, cell eating. A cell uses pseudopods to engulf something and pull it into the cell, which creates a vesicle with whatever it was trapped inside of it. Much more detail on that when we get to the immune system in Bio 139. Pinocytosis. Pino means to drink. So pinocytosis is called cell drinking. And this is a little bit misleading. I'll tell you why in just a moment. But here we have our cell, and it starts to cave in just a little bit. It creates this little cavity. Well, if I can get it to draw correctly. It creates this little cavity. And remember, outside the cell, mostly water. Inside the cell, mostly water too. But outside the cell, mostly water. And as it creates this little cavity, eventually this little cavity is going to pinch off. And inside this newly formed vesicle, there's water. But there's stuff dissolved in that water. Different types of ions and other things like that. So it is as though the cell took a drink by bringing water into itself. The reality is it wasn't after the water. It was after the stuff dissolved in the water. It's still called pinocytosis because it looks like the cell is drinking. It did bring water into itself, but it was more interested in what was in that water. Now, receptor-mediated endocytosis is very, very selective. The cells have proteins on their surface, and there's a specific type of protein that if something binds to it, it triggers this cell to start to cave in, like we just saw in pinocytosis, but at a much bigger scale. So this folds inward, it creates a vesicle, but whatever was bound to that protein is now inside the vesicle. It's been brought into the cell. It was receptor mediated. The protein was the receptor, and when something bound to that protein, it caused it to fold inward, and the cell brought it into itself, forming a vesicle. Those are types of endocytosis. Well, exocytosis is just the opposite. In exocytosis, we have our cell, we have something in a vesicle, probably some waste matter. The vesicle travels to the edge of the cell, it merges with the edge of the cell opens up, and whatever it was, the waste or the hormone or whatever, is removed from the cell. That's exocytosis. Something is exiting the cell. Transcytosis, something enters one side of the cell, travels across, and exits the other side. Maybe there's a blood vessel over here, something in the blood vessel needs to get to a cell that's over here. Well, it has to pass through this cell to get there. Transcytosis, crossing the cell. And the last thing on this slide, vesicular trafficking. If we looked at a cell and we saw all of these vesicles moving around, it looks like they're moving around very haphazard. But they're not. Inside the cell, there are actually, it almost kind of looks like train tracks or roadways or something like that. And vesicles are moving along these roadways to get to specific locations in the cell. Vesicles travel along these roadways to get to where they need to go. That is vesicular trafficking. Vesicles are moving to specific locations in the cell. Now, lastly, this is going to be kind of a big topic. We're going to introduce it here. We're going to lay the groundwork here. We are going to come back to this when we get to nerves and build on it. We are going to come back to it when we get to muscles and build on it more. We are going to come back to it in Bio 139 when we get to the heart and build on it even more. So pay very close attention here. Watch this part a few times so that the foundation makes a lot of sense. We're going to talk about membrane potentials. And we're going to introduce the topic of voltage. Voltage means that there is a separation of charges. A separation of charges. In this case, the charges are ions. Sodium, potassium, chloride, proteins with negative charges, just charged particles that are being separated from each other. And we've already introduced this a little bit. We said there is a high concentration of sodium outside the cell and a low concentration of sodium inside the cell. We said there is a high concentration of potassium inside the cell and a low concentration of potassium outside the cell. Chloride has a negative charge. There's a high concentration of chloride outside the cell and a low concentration of chloride inside the cell. High chloride outside, low chloride inside. Let's go ahead and talk about calcium. Even though calcium's not on here, this is going to be something important later. Calcium has a +2 charge. Calcium has a high concentration outside the cell, and it is so low it is practically non-existent inside the cell. We'll talk about why in our next lecture. And there are really big proteins with negative charges. We just call them anions. The A here is not a chemical symbol. It is an abbreviation for anion. They have negative charges, really big, lots of negative charge, high inside the cell, low outside the cell. Now, because of all of these different charges, and because of the separation of those charges, and because of the permeability of the plasma membrane to some of these guys more than others, what happens is there is a slightly positive charge outside the cell compared to inside the cell. The outside of the cell by itself is not positively charged. the inside of the cell by itself is not negatively charged. When compared to each other, the outside of the cell is more positive compared to the inside. The inside of the cell is more negative compared to the outside. Now we can measure this. We can measure how negative is the inside compared to the outside. And that's how it's measured. We don't say the outside compared to the inside. For whatever reason, we talk about how negative is the inside compared to the outside. And it's different in different cells of our body. We will talk about neurons, nerve cells, quite a bit in about a month or so. Neurons, the inside compared to the outside, is negative 70 millivolts at rest. Not an important number right now. I'm just giving you an example. At rest, neurons are negative 70 millivolts inside compared to outside. Muscle cells are negative 90 millivolts inside compared to outside when at rest. Different cell types have different voltages. But because there is a voltage, we say that the membrane has a membrane potential. It's due to the concentration of those ions. It's due to leaky channels that allow permeability to those ions. It's due to that sodium-potassium pump that we learned on the previous slide or so ago. But that fact that there is voltage, that there is potential at those cell membranes is going to be the driving force for how neurons and muscles and your heart work when we get there. Right now, this is just to introduce you to the idea. Later, when we get to those other body systems and cell types, we will look at how it actually works to create nerve signals or muscle contractions. Here is that sodium-potassium pump again, what we were just talking about. I won't go through this slide, but it's a good way to kind of tie all that together. How does the sodium get high outside the cell? How does it get low inside the cell? Same with potassium. And I know that was not many slides, but there was a lot of information there. So make sure to watch that a time or two more if it didn't make sense. In our next lecture, we're going to come back and talk about the organelles and what they do. And then we will have one final lecture where we look at DNA. All right, so as you watch this, let me know if you have questions. If you do have questions, don't push it aside and think that it'll catch up later. It's very important that you understand all of this because now we're getting into the stuff that really, really does lay the groundwork for the rest of the semester and beyond. All right, I hope you enjoyed the lecture. I hope you learned something from it, and I will talk to you in the next lecture.